Well, we are into the part 2 of the OWL tutorial problems. So in the last lecture, we have talked about different scenarios of modeling the statements into the corresponding OWL format. And we have made use of the functional style syntax to represent the OWL specifications, right? Now let us continue with this example, and the example says the protein lovers pizza is any pizza that amongst other things has only toppings that are both meat and seafood, right? Now if we just try to compare this with some other example that we have talked about earlier. So yeah, so this is the example. All margarita pizzas have, amongst other things, some mozzarella topping and some tomato topping. So this some is appearing before uh, both the hash topping part. So that's why we did not really represented them by taking intersection of mozzarella and tomato and then take that to be the restriction for the hash topping, right? So that was a kind of wrong representation, right? Now let us try to do something like that, right? So so you are trying to say that you have the elements. So our revised specification is that the elements that are participating in this hash topping relation. So we are basically concerned about has only toppings that are both meat and seafood, right? So so we need to have something like this. So E has topping, right? And it should be say T1, and T1 should belong to, it is a type of a meat, as well as it should be type of seafood, right? So whatever we have, so this top as topping for this E should be both meat and seafood. So that is what we are trying to model, right? So we will be modeling this as again we have done earlier. It will be the equivalent classes. So let us write it to be equivalent classes, right? And we are defining protein lovers, protein lover pizza, right? So it is an object intersection of two things. So pizza and so we should be using all values from, because we have only, right? So object all values from, and the restriction would be on hash topping, right? Restriction is on hash topping, and this topping as the restriction should have intersection of this meat and seafood, right? So we have another object intersection of embedded here. So object intersection of uh, meat and seafood. So this is going to be the OWL functional syntax style syntax representation of this text. Now coming to the first order logic form of this. So again we'll be having this both way implication, right? So our representation would be so for all P we have a protein lovers pizza, protein lover pizza P, both way implies that P is a pizza, right? and as we are having this uh, object all values from, we have to represent that using for all, right? So for all topping, if you have topping of as topping, if P has topping T, that will imply T is both meat and T is also seafood. T, right? So this is what would be the corresponding first order logic representation of this statement, right? Now, whenever we talk about complement is basically what you have a kind of class expression, you are taking a complement, right? Now, this complement can be taken over the simple class expressions like a simple class. You take say person to be a class, pizza to be a class, or it can be a complement of any class expression. So, for example, some has topping some say tomato, right? So you can take a complement of that. So that means that it does not have some topping to be tomato, right? So this complement they can combine with other expressions to make the uh, class expression bit complicated, right? And of course, while you are trying to model real world knowledge requirements, you need to have these kind of combinations. Let us look at what are the kind of different combinations we can think of concerning complement, right? Now, if we have some structure like this, object complement of object intersection of class 1 and class 2, right? So what we are saying, so in the class expression inside the complement, we have the intersection of class 1 and class 2. So if we want to represent this in say set theoretic notion, so it will be negation of the complement of class 1 intersection class 2. So this is basically representing not both class 1 and also both. It is not the case both class 1 and class 2 will be satisfied, right? Or member is both under class 1 and class 2. So this is simple set theoretic stuff, right? Now if you take the complement of union of two classes, so this means neither class 1 nor class 2, right? So again, if you represent this in set theoretic notion, it will be class 1 union class 2. So one can really draw a Venn diagram to see what kind of structure we can have for this, right? Now coming to the other cases, which are basically now we are starting to combine this complement with the restrictions, the property restrictions. So the first combination that we like to talk about is has some property that are not class. What do you mean by that? So the thing that has some value and for a particular property, and that value should belong to the complement of a given class, right? So what we are really trying to make, so you have some element E, right? An element is connected to another element, another resource via say prop relationship, right? And whatever you are having here, say O1, right? And this O1 should belong to, so it is an instance of a class, say this is a class, say C, and which is basically C is basically equivalent to the complement of class, which is basically this, right? Now, regarding the exam domain that we have discussed, one of the examples earlier, let us take an example from there, right? So I'm saying that uh, exam is something that has got participation to be some entity which is not a professor, right? So if I define this exam to be a subclass of this, if we try to define this, so what we'll have, so this E has participation to be say participation of say person 1, right? And this person 1 is a type of something, so it may be a student, right? And this student is equivalent to the complement of professor. That is what we are trying to say. Now let us see what do you mean by object complement of object some values from prop class. So that means the expression does not have any property that are this class. So again let me draw it. So you have E, right? And E has one property prop say say O1, right? And O1 is a type of say class, and we are saying this is not happening. So we do not have so this is a kind of class. So this is one anonymous class. So whatever entity like this is satisfying this particular construct will constitute a class, and we are taking the complement of this class to represent it, right? So this says does not have any property that are class, right? So so the kind of example that we can give for this particular construct is that this exam 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 is a subset of a class which is a complement of the class of entities that has got examiner to be at least one examiner to be the exam subject student or the student who are appearing for the subject. So this exam subject student is a class which is a class of the students appearing for the particular exam, right? So we do not have them, we should not have them as the examiner of the exam they are appearing for, right? So what we are doing to ensure that we are taking so this part says that we have, so these are the kind of entities which has got examiners, right? Some entity S which belongs to this exam subject student, right? And you don't want to have them, so you have all the entities like this. So you take the class of this anonymous representation, class representation or expression to be all the entities like this. If you put them together, so they will form a class, and your exam is basically a subclass of or the subset of the complement of this class, right? Where you do not have the examiners that are of student who are appearing for the subject, right? Now let us take another combination which is basically object all values from prop object complement of class, right? So that says that has only property that are not class, right? Now if we try to draw the visualization for this, so E has say property, so this P. So let me first take the example, then I'll illustrate with the example. So the example for this would be it has the exam is a subclass of something that has got the examiner to be only who are not the exam student subject students, right? So you have got has examiner to be say AS, right? And this is belongs to the class of complement of exam subject student, right? So it might be having another examiner, say S2, and S2 should also belong to this complement of exam subject student, right? Now coming to the next uh, structure or next concept expression, which is object complement of object all values from property class. So it says that does not have only property that are class, right? So we can say that exam is something that does not only contain the examiner to be the professor or the faculty, or participation to be the faculty. So we are saying that exam is a subset of complement of something that has got only participation of faculty, right? So I guess you can draw similar kind of visualization here also, right? So this is how we can combine different restriction modifiers along with the complement construct, right? And you can see that you can do many things, and depending on the combination, the semantics of the representation will be different, right? Now sometimes it is a kind of misconception that whenever we say that a particular subject has got some value, right? So at least one value or some value. So sometimes we infer that that is the only value, right? But that is a misconception. So whenever you are representing something with some keyword or existential quantification, that does not imply that only is also inferred, right? So let us take an example of this, right? So we are trying to define all margarita pizzas have, among other things, some mozzarella topping and some tomato topping, which we have already done, right? So basically it is margarita pizza is a subclass of object intersection of this part has topping some mozzarella, so some values from has topping mozzarella, and also some tomato topping, some values from has topping tomato. So this is fine, right? But that does not mean that all the toppings that this mozzarella pizza can have only tomato and mozzarella topping, right? Now if we want to enforce that, so whatever topping you can have, either it can be a mozzarella or a tomato. So here with this expression we are saying that there might be at least one mozzarella and tomato, but it is not saying that all the toppings there should be mozzarella tomato, nothing else, right? So our revised specification is so here as you see that margarita pizza, so it might be having other topping like say spicy beef topping, right? But let us rephrase or come up with a new requirement that the definition of margarita pizza that we had earlier, let that be like that. But also we are imposing the restriction that it have only mozzarella or the tomato topping, nothing else. So in that sense, this spicy beef topping is rolled out. So this is kind of thing which we call in technical term closure. So here having an enclosure between on the values that it can take only, right? So with this revised specification, the kind of representation that we'll be having, so we'll be having the thing that we had defined earlier, like intersection of some values from hash topping mozzarella, some values from hash topping tomato. So with this we are ensuring that it has got at least one topping mozzarella and another topping tomato. But this is where we are closing the thing. So here we are saying that the values that this can take as topping, they are the union of mozzarella and tomato, right? So either it would be mozzarella or tomato, but nothing else, right? So this is how we are kind of making this set to be a closed set, the value that this hash topping can take, right? Now with respect to this for all, so let us go back to the earlier slide and try to come up with some other inferences. So let's say, well, so if I just say that it is having only mozzarella tomato topping, so why could not we remove this part, right? So if we say that all values from hash topping object union mozzarella and tomato, so all the values it can take either mozzarella or tomato. So in that sense, we are kind of implying the fact that it has got some topping to be mozzarella or tomato, right? But that is not happening because of this notoricity of this open wall assumption over this particular construct for all values from, right? So the semantics or the satisfiability of the relations or the expressions that are concerning this for all has got some curious thing, right? So let us have a discussion on that. Then we'll be trying to illustrate the case of if we have this only expression in the examples, right? Or for all values expression in the example. So this is the kind of expression that we are trying to evaluate, right? So for all RC, so by this we really mean that this relation is, so for a given subject, so X and this relation R, it is having a value say Y, and this Y is a type of say C. Now it can have another value say R, say Z, and Z is also a type of C. So this is what we are representing with this formula. So for all RC, so that means the range of R for all the elements that are participating in the relation R in the subject position should be belonging to C, right? So if that is happening for a particular subject, that subject will be this X. If this is happening, then X would be a member of for all R C. So this is a kind of, this is a class, and this X is becoming a member of this class because it is satisfying the constraint or the condition that is made or represented by this expression, right? And what does it say? It says that all the objects for this relation R, all the objects. So if you have one subject which has got multiple R relation coming out of X, right? And whatever value we are having in this object position, right, or in the range, so this should belong to C. So that is what we are representing with this for all RC. Basically we are codifying the all values from restriction, right? Now whenever we are trying to uh, see what are the kind of situation where this for all RC is satisfied, so there are different cases. So in the first case, that in your knowledge base you do not have any entry for relation R, right? So you have multiple X, Y, Z, or whatever it be, but for any element you do not have any outgoing edge. So so if you take the example of X, right? So X, we have different relations like say Q, P, say S, anything, but something different than R. So R is not there. So in that case, X would belong to this for all R's. right? Second, I'm trying to illustrate the fact. So you have one entity in your knowledge base, which is X. So this is your X, which is there in your knowledge base, right? And it has got many relations, say Q, P, and others. So let us take these are the two relations that are coming out of X, right? And you have got Y1 and Y2 as values, right? But it does not have any relation with R. So this R is not there. In that case, X would be a member of all R's, right? So this is what we call as uh, mm, this is also in this case we see that this particular expression is getting satisfied, but it is satisfied trivially or vacuously. So this is called trivially satisfied. Trivially satisfied. So we do not have any case for R, still it is satisfied, right? The other case is there are entries for relation R in KB. So you have different entities, say Y, from where you have got outgoing relation R, right? So in that case, there will be two situations, right? So here we are satisfying this particular case is satisfied. Now let's say for X we have got these two relations coming out of X, and they're going to Y. So what we have, X R Y1 and X R Y2, right? Now here we have two cases. So one case is that for all yi, they belong to C. So these are types of C. So in that case, we say that in my knowledge base, given my knowledge base, this expression for all RC is satisfied, right? The other case is if you find at least one yi, if you find at least one yi, let's say you have this y1 to belong to C, type of C, and y2 type is say D, and C and D are disjoint, right? So in that case you have at least one yi which is y2 which does not belong to C. In that case you say given your knowledge base, your for all RC is not satisfied, right? So this is what we this is how we interpret for all RC in open world assumption. So this trivially satisfied thing is really considering the fact that in this particular scenario, you do not have any outgoing edge from X with R level, but in future you can have that. So you put that to be your case of satisfied, right? So this is how we interpret trivially satisfied case with respect to the open world assumption. Now, as we have mentioned earlier that some does not imply only. The other way is also true, that only does not imply some, right? So to illustrate this, let us take an example where we are trying to define the vegetarian pizza, that is any pizza which amongst other things has only topping that is not meat, and also that is not that has only topping that is not fish. So this is very easy to implement. So this equivalent classes, veg pizza is equivalent to the intersection of pizza and something that has got all the toppings that are not meat, and something that has all the toppings that are not fish, right? So this is what we are trying to model, right? Uh, Now, if we have the definition of an empty pizza, so what would the definition of an empty pizza will look like? So the definition of the empty pizza will say that all empty pizzas among other things do not have anything as topping, right? So what would be the corresponding functional syntax representation for this? So empty pizza is a subclass of pizza, so we can name it as equivalent class. That does not really matter. So empty pizza is an intersection of pizza and object complement of some values from topping thing. So it has, so here we are ensuring that something has got topping to be theme, and we are taking the complement of this, right? So here we are just trying to say that it, so if we go by the semantics of all values from, right? If we go by the semantics of all values from, so even if your pizza, your this definition of the veg pizza, this pizza does not have any topping, this will also be satisfied, this will also be satisfied. And here also we are having the same kind of definition where we do not have any topping, right? So you see, these two representations are coming to be more or less equally interpreted, right? So here also we have a case, we do not have anything as topping, and here also if a particular pizza do not have any topping, that will also satisfy this definition, right? So in some sense, this veg pizza is going to be equivalent to empty pizza, which we do not really want to do, right? So, so that brings us to the case that even though you have said that it has got all values from something, so it means that the toppings they are belonging to some particular class, right? And all the values that the topping can take, they are not met, but that does not ensure that you'll be having a topping. So even if you do not have a topping, this will be satisfied, this will be satisfied, and in that logic this empty pizza will also be termed as a veg pizza, right? So if you do not want to do that, so you want to really come up with the proper definition of this veg pizza. So here, along with this all values from, you have to also say that it has got a topping. So you need to append something like this: object some values from has topping, and then it would be owl theme. So it will make sure that it has got at least one topping, and if you do that, then this empty pizza will not be equivalent to your veg pizza, right? So you need to be very careful after we have declared that a definition of a pizza with all values from construct, that does not ensure that that will imply that there is some topping, right? So this is a kind of modeling error sometime you may come up with. Now, there might be confusion between some not and not some, right? So, if we try to define the vegetarian pizza, which is any pizza that amongst other things both has some topping which is not meat and also some topping which is not seafood, right? Now, if we try to model this, so what would be our uh, mm, definition or our representation in functional syntax style, right? So we'll be using equivalent syntax, equivalent classes, right? So let us name it to be veg pizza W. So we are using W with an intention that will be clear for some time. Now this is object intersection of pizza, right? And some topping which is not meat, right? So object some value. So we are modeling this part. Object some values from some values from has topping. So has topping, and what will be there inside? Will be having object complement of meat, right? It will be complement of meat. Object complement of meat, right? So you can close this part, okay, right? And this, right? Now there would be another object some values from object some values from, right? And it will be on as topping, right? And it will be object complement of fish, seafood, uh, seafood, right? We have closed this, we have closed this, we have closed this. I think we should have another, right? Now we have closed this, and finally we have closed this, right? So this is the definition of veg pizza according to this, right? Which says that it has got at least one topping which is not meat, right? So let us try to draw a visualization for this. So you have a pizza, right? And it has got topping to be, say, tomato, right? So that means it has got a topping that does not belong to meat and that does not belong to seafood, right? So in that sense, you can say that this P would belong to veg pizza W, right? That is correct. But if we have another relation like as topping, say, crab. Now the question is whether this P, whether this P would be a member of veg pizza W. Of course it would be, because you see these some values from it will be satisfied if you have only at least one relation coming out of P which has got a value. I should not have written the thing like this. So let's say it has got topping to be, say, T1, and T1 is a type tomato, right? And it is T2, and T2 is of type crab, right? Now you see that this this condition and this condition is being satisfied by this relation, right? So you have at least one relation out of P which has got a value T1 and it is having of type which is not meat and also it is not seafood, right? So in that sense this will be satisfied irrespective of whether you are having another topping which is of type meat or seafood. So this is a wrong definition of a veg pizza, right? So according as per your definition, this P would be classified into veg pizza, but you see this is a wrong definition of veg pizza. If you want to correctly define it, so what would be, we need to really exchange the position of the some and not. So you should say that has do not have some topping that is meat, or do not have some topping that is seafood, right? So our revised definition of veg pizza is vegetarian pizza is a pizza that amongst other things both does not have some meat topping and does not have some seafood topping, right? So you see we have exchanged the place of some and not, and you see by just exchanging the place we are having a different definition, and one is correct, other is incorrect. So for the sake of completeness, let us try to draw the equivalent functional syntax style representation of this, right? So equivalent classes, and you have this veg pizza, the correct definition of the veg pizza, which is object intersection of pizza. So we'll be flipping the position of the complement and the restriction modifier, right? So pizza object complement of, we do not have any topping, meat topping. That is what we are trying to represent. Object complement of, right? And it will contain as input object some values from uh, and this restriction would be on hash topping, and the value would be meat, right? So it does not contain any topping that is meat, right? So that is how we are representing, right? And also object complement of the second part, object complement of object some values from hash topping, so it will be on hash topping, and here the argument would be seafood, right? So one more, right? So this is the correct definition of veg pizza. Now let us come to the examples of cardinality, right? And we know that the cardinality is really counting the number of same relation coming out of a particular subject, right? So that is what we call cardinality of that relation with respect to the given subject, right? So we are defining the class of interesting pizza, right? So the interesting pizza is any pizza that among other things has at least 3 toppings. So it is the case of what? It is the case of simple cardinality. Simple cardinality, right? And which is not really having one class expression to be the restriction class, right? So that is not there. So if we would have that kind of thing, that was to be called as the qualified cardinality. So here we are talking about only simple cardinality, right? So how do we represent this? So we are having equivalent class definition. So equivalent classes, interesting pizza, and it is equivalent with the object intersection of, right? Object intersection of pizza Now coming to the cardinality. So we represent that with, we are as saying at least we'll be using mean cardinality. So object, so this is also a restriction class, right? So this is also a restriction class, right? So object mean cardinality, and the restriction is on hash stopping. The value, that the number of such relation that can go out from a subject which is belonging to this class would be 3, right? So 3 hash stopping, right? So if we would like to draw the corresponding first to the logic representation, what would it look like? So we are defining the interesting pizza. So for all p interesting pizza, pizza p both way implies that it belongs to pizza. And now how do we represent this at least 3? So we assume that there is at least T1, T2, T3. There are 3 toppings where you have got hash topping PT1 and hash topping PT2 and hash topping PT3. Along with that, you need to say that T1 not equal to T2 and T2 not equal to T3 and T1 not equal to T3, right? Now, how do you represent that any pizza among other things has at most one pizza base, right? So, at most once we can represent with max cardinality, right? So, what we are trying to represent here, we are here, this is a case of subclass, right? So, we are representing this with subclass of pizza. So, pizza is a subclass of something that has got at most one pizza base, and whenever we use this term at most, we'll be representing it with max cardinality, nullity, right? So subclass of pizza is a subclass of object max cardinality. The cardinality value would be 1, max cardinality value would be 1, the limit would be 1, and this will be on hash base property, right? Now, how do we represent this in first order logic? So, for all p, right, if something is a pizza, if p is a pizza, then so we'll be again modeling this as assuming that it has got 2 pizza bases, b1 and b2, and b1 not equal to b2, right, and hash base p b1 and hash base p b2, and this should not happen, right? So that's how we are restricting the value of the number of bases to be 1, right? Now, how do we represent reflexive property in our, right? So let us try to model this. Modest are those people who do not praise themselves, right? So here we will be using the fact that we can define a property to be reflexive property, right? So let us see how do we model it. So equivalent classes, right? So we are defining modest person, right? So it is intersection of object intersection of person and mm, now the next part, who do not praise themselves, right? So how to represent who do praise themselves? So you'll be writing object has self, right? So has self is basically representing that a particular property is reflexive, and we'll be putting this relation like praise to be the argument of this. Well, by this we are saying that praise is a reflexive property. So and we need a complement of this, right? So the persons who do not praise themselves. So so object complement of complement of, right? We have closed this, close this, close this, and close. Right. Now, how do we represent this in first order logic? So we are defining the modest person, right? So for all p modest person p, both by implies that p is a person and p does not praise himself. So how do we do that, or herself? Praise p, right? Now in some cases we want to use this universal quantification, right? So but also at the same time we want to say that that is the kind of thing, so that there is nothing else. So let me try to take this example to illustrate the thing, right? We are saying that all old ladies must have a pet and the pets can only be cats, right? So we could have modeled this as say this old ladies, they are a kind of subclass of something that can have pets only to be cat. But as you know, with the semantics of this open world assumption, and concerning to that the semantics of the for all operator. So even if you do not have any cat, that will be kind of satisfied trivial. Actually, you don't want to do that. You want to say that it must have a pet, and also this pet can only be cat. So that is what we are trying to model, right? So you see that here, in one sense, we will be using the existential quantifier. The other sense we will be using for all quantifier. And here, this existential quantifier in the range, we do not specify any class. We are not saying that this pet can be a class. It has got these old ladies, they have only a pet, only one pet, or at least one pet, right? And we are not saying which class does this pet belong to. But in other statement, you are saying this pet can only be cat, right? Now the other kind of logic we could have provided that well, if we have just said that all old ladies must have a pet to be cat, right? So all old, so let us try to take different versions of this. So first version says all old ladies must have a cat as pet, right? Now we can represent this with say existential quantifier or some values, right? Now this does not ensure that this lady, one lady cannot have more than one pet in the first place, and in the second place, the pet, it can be something other than cat. In that case also, this particular statement would be satisfied, right? So that's why we cannot just use only this existential quantifier to represent what we are trying to say. Now look at the other way of modeling, right? So this all old ladies have pet to be all cats, have cats only as pet, right? So here we are trying to model this with universal quantity, right? Now this means even if the lady does not have any pet, this will be satisfied. So that's why to safeguard this, we need to have the other quantification existential quantifier to be in place. So this will ensure that the old ladies has at least one cat. Now coming to the second part, if it is having a cat, then it should be if it is having only a pet, only having a pet, this pet should be cat. So you need to combine these two together to come up with the representation of this statement, right? So we are not providing any sufficiency condition, so it will be a case of subclass, right? So so we are representing a subclass of old lady, right? And this object intersection of uh, object some values from, we are using the existential quantifier, some values from, right? And it will be having has pet to be something. So we'll just say owl thing. Sorry, we'll be having owl thing. So one pet, right? And object all values from the other part. Object all values from has pet to be cat. So this is, we are ensuring that the pet that she is having is a cat, right? So we'll be having, okay, I guess we are done. Okay. So if we try to represent this in first order logic, so this is what we'll be getting. So for all L, old lady L implies that there exists a pet P has pet, I'll say P1, has pet L P1, and for all P2 has pet L P2 will imply that P2 is a cat, right? So that is how we can implement.